going to talk about some of the protection design aspects in terms of wildfire risk. And this is a work that my former student Tauhid did. He's also here. Thank you. So I'm going to keep it short, like quick introduction. So around 15% of the wildfire events are technically named utility cost, are caused by utilities, electric power utilities. But those wildfire events actually incur a lot of penalties for electric power utilities, and it's very important for them to avoid that. Yeah, and then you can see on that graph that, for example, starting from 1995, these incidents started, and then have been increasing over the technically past 25 years. Yeah. And in the US, 10 out of the most destructive California wildfires were actually utility cost from an issue in the electric power utility. And yesterday, we had the presentation from Brian from SDG&E that talked about these issues in SDG&E territory, and also, yeah. Oh, yeah. So, yeah. Good. Thank you. Yeah, and also in the morning, we had the session that they talked about the modeling and approaches for wildfire, very useful. So what are these utility cause wildfires? Yeah, so different factors actually contribute to the a power grid to cause a wildfire. For example, high winds, vegetation contact, down power lines, and then animal contact, arcing, equipment failure, and also the protection devices like fuses and reclosers, which is technically the focus of my presentation. And this is more likely to happen in distribution power grid. Why? Because we have a closer proximity to the source of technically fire, which is vegetation, and more exposure. And then pole and ground fires due to equipment related failures are very common. But what is the utility response? Usually, I think it was also mentioned yesterday, utility response is usually PSPS, yeah, public safety power shutoff. And it could be very effective because technically all the cool models and technologies that were presented in the first session today can be used to identify these high fire threat districts, yeah. And then based on the utility decides if they need to do PSPS or not. And then they come up with very cool algorithms and techniques to make a decision. It's a very hard decision. Why? Because the outcome is technically shutdown of power to the customers. So even though this decreases the risk of wildfire, on the other hand, the issue is that we will have a very poor reliability in the system during that period of time that we have the risk of wildfire. And as I mentioned, this is actually more technically a more challenging distribution systems rather than the transmission level. So what can we do in terms of the power system design to decrease technically the PSPS, technically the number of PSPS that can happen in the utility during like September, October in, for example, San Diego, which is the months that we can have lots of wildfires. So one approach is super fast protection devices. And in distribution power grids, I think Fanush actually had a very cool graph because we have short electric distance. The problem is that detecting traveling waves, which can enable us to have fast tripping protection schemes for finding or detecting the falling conductor or detecting the high impedance faults in the system. Having that in distribution system is super hard. What will be the solution? The cool sensor that Farnush presented. Yeah, and we did that actually a study supported by Department of Energy in collaboration with Sandia. And we found that actually in order in distribution system to identify falling conductor or faults, technically we need to have that microsecond of technically time step in the data measurement, which was technically that 1 million data samples should be measured every second. All right. But the other thing is to technically, when we design a part of the system, to properly design in terms of putting the in terms of finding the location of the protection devices in order to decrease the risk of wildfire. And that's the focus of this presentation. Two of very common types of protection devices in distribution systems are reclosers and fuses. Yeah, so fuses, very simple technology. They are not selective. When they see a fault, when we have a fault, based on their care, they are going to operate with some delay. And then reclosers, what they have, they are being operated by usually a time over current element. And then they have this reclosing option. Reclosing means that 70% of the faults in power grids are temporary. Yeah. So, and temporary faults, for example, like assume a bird technically flying, sits on a power pole, spreads the wings. We have a fault. Fortunately, the bird dies, falls. The fault is cleared. That happens a lot. Yeah. For the bird. Unfortunately for the bird. Yeah, I've seen pictures of eagles actually because like, they have like big bodies. Unfortunately, they die because of this. So the fault is temporary. If we have a fuse, the fuse operates. Yeah, the fuse doesn't care. It operates. So the customers that are downstream of that area, technically they lose their power. So what recloser does, it provides the reclosing option. Yeah, so it detects the faults, waits, then opens the breaker, then recloses again. Then waits for 10 to 30 cycles. And it depends number of shots. It could have a single shot or multiple shots. And then based on that, if the fault is permanent, we'll permanently open the breaker. But if the fault is temporary, then technically the fault is gone. We don't need to technically cut the power to the customers that are downstream. Yeah. And here in this slide, you can see the impact on reliability indexes. So SAFE technically with, oh, and I forgot to mention, the other thing that we can have for the fuse and recloser is these two schemes, fuse blowing scheme and fuse saving scheme. So in fuse blowing scheme, the recloser lets the fuse blow. It doesn't care if the fault is permanent or temporary. But in the fuse saving scheme, the recloser has some mechanism. I don't go through that. What it does, it lets the fuse not to operate if we have a temporary fault. Okay, so technically the fuse is safe. And that will drastically increases the reliability of the system. You see the SAFE with the fuse saving is much lower, but MAFE, which is technically the momentary interruptions, technically is higher, but the technically long-term interruptions with fuse saving is much lower. But the problem is that fuses technically have two main technologies. Some of them are explosion type, some of them are non-explosion. Explosion type fuses, they are a risk for wildfire. Yeah, because we have explosion, arc is exposed to the vegetation. Reclosing also is a risk to wildfire. Why? Because whenever fault occurs, the recloser recloses, the fault is energized again. We have an arc. If we have like in September high vegetation, that increases the risk of the wildfire. So technically this figure shows like, yeah, with fuse blowing, fuse saving. With fuse saving, technically we increase the reliability, but on the other hand, we increase the risk of wildfire. So what we did as part of this project, we created an optimization algorithm to find, let's assume that a utility on a distribution feeder, they are like building a new distribution feeder, and then they want to install like, I don't know, 4 reclosers and 8 fuses. Where to put those devices to, while increasing the reliability of the system, also decreasing the risk of wildfire. And for that, what we did, we created some objective functions. Yeah, we have a reliability part, which is based on SAIDI or SAFE, and then we have a wildfire part. And based on that, we define the wildfire index. And technically, that wildfire index depends on 2 technical factors. The location of the fuse, because if we have an explosion type fuse, when the fuse operates, we have risk of wildfire on that location. And also the other index, which is that index is called technically fuse index. The fuel index is technically because of the location of the fault, and the reclosing that increases the risk of fire at the location of the fault. Yeah. So based on that, we define in these indexes, and they depend on the vegetation. Came up with some vegetation factor, and we came up with like an overall technically wildfire index, which also depends on the fuse scheme, fuse blowing and fuse saving scheme. And then we define an overall objective function. I want to keep it short. So this is the overall optimization algorithm. What we do, we come up with some initial locations, some protection zones, push it into an optimization algorithm, and the optimization algorithm, what it does, tries to minimize that objective function. So at the end of the day, we have the locations, good locations for fuses and reclosers that minimize the wildfire risk, maximize the reliability of the distribution system. And we implemented that on IEEE 123 node system, which is like a test distribution system from IEEE, and then we define these vegetation factors and for each line, and the restoration duration for SAIDI and SAFE. And then finally, you can see some results here. So we ran this for technically two number of fuses, 6 fuses versus 8 fuses, and the number of reclosers 4, 5, and 6. Here you can, I actually gave the team another slide to identify these clusters, but if you see on each of the graphs, the left one is for fuse blowing, the right one is for fuse saving. On the left, the cluster on the left technically is for the case that we have 6 fuses, and the cluster on the right in each of these graphs is for the case that we have 8 fuses. Our fuses here, we assume that they are explosion type. So if we increase the number of fuses, we get a higher technically wildfire risk, which is on the x-axis. On the other hand, the technically the number of reclosers, as the number of reclosers increases, we also get a higher risk for wildfire. And the other thing that we noticed was that in fuse saving, we usually get a higher wildfire index. And the reason is that in fuse saving, we have more number of reclosing because the recloser tries to save the fuse by more number of reclosing shots, and that increases the risk of wildfire. So technically that what utilities currently do when there is a risk of wildfire in their system from the technically substation somehow remotely, or they need somebody to the field, they technically stop the reclosing option on the reclosers. But if we can have a way to have good location for reclosers to minimize the wildfire risk, technically we don't need to do that, because if we disable the reclosing function, then we have a poor reliability. I think that was it. Thank you very much for your time.